Let's rewind the clock for a second, all the way back to 2014. Something pretty incredible happened in the world of AI. A team at Google DeepMind published a paper that, for the very first time, showed an AI that could learn to program itself just by looking at examples. So how on earth did they pull that off? Let's break it down. To really get this, we need to start with a super simple question. Just imagine, what if you could give an AI a notebook and a pencil? What could it learn to do if it could just jot things down? Believe it or not, that simple idea is the key to this entire breakthrough. You see, up to this point, neural networks were basically pattern-matching superstars. You could show one a million pictures of cats and yeah, it would get really good at spotting cats. But if you asked it to do something that required a sequence of steps, like following a recipe, or even just remembering a phone number you just told it, it would completely fall flat. It's not that they had zero memory, but it was all kind of jumbled up, not organized like a list you can read from top to bottom. So the researchers' solution was a brand new kind of AI architecture. They called it the Neural Turing Machine, or NTM for short. And the central idea? You guessed it, it all came back to giving the AI its very own external notebook. Okay, so let's look under the hood here. First, you've got the controller, which you can think of as the AI's brain, and it's hooked up to this external memory bank. That's our notebook. Now, to actually use the notebook, the controller has special tools, read and write heads. These are basically its eyes and its pencil, letting it scan for information and write down new stuff. Let's make this even more obvious with a direct comparison. The controller is just like the CPU in your computer, or maybe the central executive in your brain, the part that's focusing your attention right now. The memory matrix is basically RAM, or just a simple notepad. It's a blank slate ready for information. And the read and write heads are the tools for interacting with that slate, like your eyes scanning a page and a pencil taking notes. The whole point is we've finally given the AI the basic tools of computation. So how does this all work together? Well, it's a simple, continuous four-step loop. First, the controller gets some new piece of info. Second, the heads focus their attention on a specific spot in the memory notebook. Third, they either read what's already there or write something totally new. And finally, the controller uses that info to produce an output. And this just happens over and over and over, which allows the AI to tackle really complex, multi-step tasks. But here is the absolute magic that makes it all click. The entire system is something called differentiable. Now, that is a fancy math term, but what it means for us is actually beautiful and simple. The AI can learn from its own mistakes. If it gets an answer wrong, the system can send an error signal all the way back through every single part, the controller, the heads, the memory, and everything adjusts itself just a tiny bit to do better next time. It literally learns how to use its own notebook all by itself. So the idea is brilliant on paper, but you know how it is. Does it actually work? The researchers put it to the ultimate test with one massive question. Could this AI really, truly learn to program itself from scratch? The first challenge they gave, it sounds almost ridiculously simple. The copy challenge. All the AI had to do was look at a random sequence of data, and then spit that exact same sequence back out. Easy for a regular computer, sure, but could a neural network learn the procedure for how to copy? And the answer was a huge, resounding yes. This visualization is so cool. It lets us peek inside the NTM's notebook as it works. On the left, you can see the right head moving from one spot to the next, like a typewriter, carefully placing each piece of data in a new slot. Then, look to the right. The read head follows the exact same path to pull the data back out in the right order. This is the smoking gun. It didn't just memorize the pattern, it learned the algorithm. Right, move, then read, move. And hey, don't just take my word for it. The researchers themselves confirmed it. They wrote that the sequence of operations performed by the network can be summarized by pseudocode. Let that sink in for a second. The AI wasn't just finding patterns anymore, it was generating a step-by-step program. Okay, so copying is cool, very cool, but let's crank up the difficulty, right? What about something much harder, like sorting a list of items? This requires more than just storing and retrieving. It requires organizing things based on rules. And honestly, the results here were just incredible. The AI was given a list of items, and each item had a random priority number attached to it. On the left, you can see the AI writing the data to its memory, but look closely. It's not just putting them in one after another. It's inventing its own little filing system, placing each item in a specific location based on its priority. And then, on the right, it reads them all out in perfect ascending order. It taught itself a sorting algorithm. That's just wild. But see, the real power of learning an algorithm isn't just about solving one specific problem. It's about being able to tackle problems you've never even seen before. This is the real superpower we're talking about, generalization. So this leads us to the million-dollar question. The AI was trained on sequences that were, at most, 20 items long. So what happens if we throw it a curveball? Can it handle a list that's way longer than anything it's ever practiced on? This chart tells the entire story. On the left, you see all those scattered dots. That's the error rate for a standard, powerful AI called an LSTM. As soon as it saw longer sequences, it just broke. The errors went through the roof. But now look at the NTM on the right. That tight, clean line at the bottom means its error rate stayed incredibly low. Why the huge difference? Because the standard AI had only memorized patterns, and those patterns fell apart. But the NTM, it had learned the method of copying. And that method works no matter how long the list is. It really is the classic difference between just cramming facts for a test and actually learning the formula. Once you know the formula, you can solve any problem they throw at you. So why does all this matter so much? This wasn't just a clever engineering trick. It was a real conceptual leap forward, a huge step towards a fundamentally smarter kind of artificial intelligence. And the paper ties this right back to you and me. The authors state that this whole process is incredibly similar to what psychologists call working memory. Our ability to hold and shuffle information around in our heads to solve problems. This AI was developing its own synthetic version of that. All right, let's recap the whole breakthrough. The key idea was simple but profound. Give an AI an external notebook that it can actually learn to control. The key result was the proof. This AI learned actual, real algorithms just from watching examples. And the key impact? It's massive. This research paved the way for the modern AI we have today that can reason, plan, and work through complex multi-step tasks. So back in 2014, this paper proved that an AI could learn the fundamental process of how to compute. And that leaves us with a really big question for today. Now that it can learn to program, what will it learn to do next?